Okay, so in the last video we saw about the Newtonian equation of viscosity. So now in viscosity, that is one part. The next part is Poiseuille's equation. Poiseuille's, is the spelling correct? Yeah, you add an I here. Poiseuille's equation. Okay, Poiseuille's equation. So Poiseuille said, if the volume of a liquid is flowing through a tube having radius r and length L in time t, the pressure difference between the two ends of the tube can be given as delta P, that is equal to P1 minus P2, and he gave an equation. Okay, how did he give? He told when a certain volume is flowing in a time t, he gave the pressure difference as this. Now pressure difference is this now, delta P over L, and there's a certain constant. The constant is pi r to the power 4 over 8 eta. Now this equation is called Poiseuille's equation. This equation you should remember, pi r to the power 4 delta P over 8 eta L. This is equal to V over T. Now in fluid dynamics you might have learned the equation of continuity. Equation of continuity is when you take something like this and radius r, no, take this area as a1, this area as a2. If the fluid is flowing in this direction with v1, if this is with v2, as this is in the same horizontal level, we can apply equation of continuity. Continuity, that is a1 v1 equals a2 v2. We call this a1 v1, so we can say av is a constant, right? So this constant you call it as flow rate, q dot, v over t, volume and t. This is velocity, this is volume. Okay, volume over t. How did you get this? Now you know velocity is distance over time, right? So this distance, this is L, so L over t. Velocity is L over t. So A into L over t. What is A into L? A into L. That is the volume, V, capital V over t. So this is called flow rate, volume flowing per second. When you divide it by time, you get the value as volume of liquid flowing per second. That is the flow rate. So this is also a flow rate, right? So they might connect you with this, with fluid dynamics. They might give you areas, and so you can say A into simple V is equal to pi r to the power 4 8 eta L delta P over 8 eta L. They might give you this also. Okay, so this equation is Poiseuille's equation. This equation is equation of continuity. This can be applied when there is no, if you consider this as if the tube is opening at one end and closing at one end, and if both the ends are in the same horizontal level. You can't apply equation of continuity for a tube like this. Why is that? If you consider this as zero potential level, there is a certain height. So you can't apply this equation here. This equation can't be applied here. For this you apply Bernoulli's. What did Bernoulli say? P plus half rho v squared plus rho gh equals constant. The total pressure over here is equal to total pressure of here. Something like energy. Kinetic energy plus potential energy here will be equal to kinetic energy plus potential energy here. But additionally, because there is a flow, there is an additional pressure. There is an additional pressure. So this is the Bernoulli's equation. Okay. So that's it. And they might ask you to prove this equation using dimensional analysis. So if you know the dimension of this, then you can easily prove that Poiseuille's equation is dimensionally correct. You know LHS equals RHS, and then equation is dimensionally correct. That's how you prove it. There was this equations like that. You can check it. The Roman number 1 was that. That is equation. Now, now if there is a law or if there is an equation, there should be conditions, right? So conditions for Poisson's equation. Okay, conditions for Poisson's equation. What is the first condition? There are four. Okay, there are four conditions. The very first condition is the flow of liquid should be a laminar flow. Laminar flow. Laminar flow means streamline. Streamline flow. Okay. For this, to achieve this, the liquid should flow under low pressure difference. If you can remember, I told you in the last video, if delta P is greater than a certain value x, then this will be a turbulent flow. If delta P is smaller than a certain value x, this will be a laminar flow. So this is applicable for this, not this. Okay, not this. So this is applicable for this. So under low pressure difference only you can get a laminar flow. If you didn't get a laminar flow, if you're getting a turbulent flow and you still want to verify the Poisson's equation, then what you do is lower the pressure difference between the two. Okay, and the second thing is it should take place under steady conditions. Steady conditions means the flow should be a steady flow. Steady up. Okay. The third one is the liquid should be incompressible. That means when you apply a pressure, the liquid shouldn't reduce its volume. It should be incompressible. Then only the same volume will be flowing. Or else how can you apply this equation? How can this volume be constant if the liquid is getting compressed? If the liquid is getting compressed, this volume will reduce. So this equation will be invalid. That's why that is a condition for this equation. Okay, it should be incompressible. Incompressible liquid. Okay. Fourth one, now all it is they are talking about the liquid. The last one only they are talking about the tube. The tube in which the liquid is flowing should be horizontal. I told you it should be horizontal. Same potential level here. It should be horizontal and it should be narrow. These are the conditions. If they ask you in the essay question, what are the conditions for Poisson's equation? The flow should be a steady flow, a streamline or laminar flow. The liquid flowing through the tube should be incompressible. The tube should be horizontal and narrow. These are the four conditions. Now we'll consider a tube like this. It is having area A1. This area is constant. Okay. We also A1 only. Constant area. This is having the flow of the liquid with velocity v. So when you consider a certain part like this, the flow rate of this liquid is q dot. Q dot is v over t. Okay. Here v over t, that is only I take it as q dot. I have mentioned as q dot. Q dot. It used to represent the flow rate. So and the pressure difference is here P1, here it's P2. So the pressure difference is P1 minus P2. Okay. Now if you find rate of work when the viscous fluid is flowing along this tube. Okay. Now rate of work, what do you call a rate of work? That is the power. Rate of work, if it is rate something, if you consider x, if it is divided by t, this is rate of x. If x is divided by distance L, this is gradient of x. I told you delta v over delta d. D is L now. So velocity gradient, delta p over L, pressure gradient. This is rate of x. So rate of work done means work done is what? Energy. So energy over time. Rate of work done is this. This is power. Okay. So power can be also written as energy over time. Energy is what? Work done. Work done is force into distance. Force into distance over time. So if you consider this to S over T, what is S over T? Distance per unit time. That is the velocity, FV. Okay. Fv. This is velocity and this is force. P equals Fv. You should be learning this in mechanics. Okay. Now you know, if you consider force, what is pressure? Pressure difference. Because of pressure difference, only know this is moving. Pressure difference is force exerted per unit area. Okay. So if you take force as subject, force will be equal to delta P into area. Okay. And then I told you equation of continuity, AV. AV. So I told you that is equal to flow rate. Q dot equals AV. Okay. Q dot equals AV. So what is V? If you subject V, V equals Q dot over A. Now you take this and subject the force from this and the velocity from this. So power will be equal to force, that is delta P into A, delta P into A, multiplied by velocity. Velocity is Q dot over A. So area cancels, delta P over, sorry, delta P multiplied by Q dot. This is the power. This is the rate of work done when a viscous liquid is flowing through a tube. Okay, this is power. See, power. Okay, so with this they might ask you questions. They might give you the flow rate directly, or they might give you area and velocity and force. Sometimes they might not give you the area, because area and area can get cancelled. This they will give you only force and the velocity. Then directly you can apply this. No, that mati taruna. Okay, you should be able to solve. Okay, now we'll consider combination. Like now all this time we studied straight this thing like this Baba cable. But what if there was another tube attached like this? And if they ask you to find the pressure difference, if this is P1, P2, P3, and if you ask them to find the pressure difference of this, how can you find? We'll say that. We'll see that later. Okay. So since I don't have space in that page, I'm going for a new page. So this is the tube going like this. Okay. And it is having length L1. This length is L2. Pressure P1 here, P2 here, P3 here. Area A1. This area is A2. Uniform area. Okay, from here to here same area, and from here to here same area. But this area and this area is different. You can see the diagram itself now, clear now. And when you consider the flow rate, in flow rate it doesn't depend on the area. It just goes like that. Why? AV is constant. If area is decreasing, the velocity should be increasing. So now here there's a bigger area, here there's a small area, but you can't say that Q dot is decreasing. You can't say this. Q dot is constant. Why? If the area here is lower than this, velocity of the fluid over here should be greater than the velocity of fluid here. That's why AV is constant, equation of continuity. Velocity of this should be greater than the velocity of this, because this one's area is greater than this. If you still didn't get what I told you, write A1V1 equals A2V2 and you will understand. Okay, that is in fluid dynamics. This is viscosity, so I'm not going to explain that. And how can I say? Okay, so what did Poisson say? Poisson said Q dot. Now here also it's Q dot. Here also it's Q dot. Flow rate along the same tube in the horizontal level is same. Q dot equals pi r to the power 4 delta P over 8 theta L. This is important. Okay, now we want to find the pressure difference for the whole composite side tube. So how do you do that? First, subject delta P from this equation. Delta P will be equal to Q dot 8 eta L over pi r to the power 4. Okay, now this is area A1. Now take the radius of this as R1, radius of this as R2. Okay, now we'll apply from here to here first. Here to here, what is the pressure difference? P1 minus P2, that is equal to Q dot 8 eta L1 divided by pi r 1 to the power 4. Now from here to here, if you apply, P2 minus P3 is equal to Q dot 8 eta L2 divided by pi r2 to the power 4. Now what will happen if you combine this? If this is the first equation, if this is the second equation, if you add these two, you get P1 minus P3, right? What is P1 minus P3? Pressure difference along the compositor. So that will be equal to Q dot 8 eta over pi L1 over R1 to the power 4 minus L2 over R2 to the power 4. For MCQs, if you can't remember this, you can directly derive it from here, but it will take no time. Intelligent students, remember this. That doesn't mean you're intelligent. It can mean you're lazy also, but yeah, for saving the time, their intelligence in saving the time. So they remember this. If you want, you can remember, or you can derive it. Okay. That's all. That is all for the coefficient of viscosity. Sorry, that is the Poisson's equation. After that, we have Stokes' law.